Okay, great. Then, welcome everybody to the first lecture of algorithmic meta-theorems. I'm happy to see that so many people are turning out for what is the first lecture of algorithmic meta-theorems. Of course, I would be very happy to have as many people of you in the room instead of offline, because it makes the communication easier. And I think with such a small group, we can have some active discussion going on, people asking questions, clarifying things. And yeah, after such a long time in isolation, it would be nice to see people again. I hope you all agree to that. And yeah, for those participating remotely, maybe they want to put on the camera, then we can see a little bit of each other as well, nevertheless. Okay, great. Then let's get started with the content. So this is more of an introductory lecture today first. I'll explain a little bit what it's going to be about, and then about how it's going to be organized this semester. And then hopefully in the second half, we will already start to see some first examples of what's going to happen sometime soon. Okay, so maybe let's start about what are algorithmic meta-theorems and why should you care about them and what's going to happen in this lecture. So algorithmic meta-theorems kind of lie at the intersection between algorithms, graphs, and logic. So if you're into that, then you may also enjoy what we're going to talk about next. And in the words of Stefan Kreutzer, he says, algorithmic meta-theorems are results of the form every computational problem that can be formalized in a given logic L can be solved efficiently on every graph class or in every class C of structures satisfying certain conditions. So this is like a one-sentence definition. So let's maybe break it down a little bit. So first of all, it says that we're going to talk about problems expressible in a certain logic. So instead of just using English to define our problems, we're going to use some logic, first-order logic, second-order logic, most in this lecture. We're going to define it when it comes to time. And we also require restrictions on our inputs. So we usually work with graphs. And this is because the problems that we want to deal with in general, they would be hard, but we try to restrict our instances in such a way that the problems become tractable. And we try to find the least restrictive restrictions such that you can still solve a whole bunch of problems. And if we're going to talk a bit more about the specifics, then one thing we're going to learn to do is how to express certain graph problems in logic. So for this, it's mostly going to be MSO, monadic second-order logic, and first-order logic, which we're going to define soon. And once we know how to express these problems, we can evaluate these formulas. So on tree-like graphs, we will learn how to evaluate MSO formulas. And if we can evaluate these formulas efficiently, then we can also evaluate all these problems that are expressible in the logic efficiently, and then we get our meta-theorem. Okay, for tree-like graphs, that's going to be tree width. I'm not assuming you guys to be familiar with all this, so some of you may be already, but I'm not assuming any prerequisites beyond bachelor level for this course. One more thing which I forgot to mention, if you have any questions, I may not see it in the chat, so maybe just speak up and then we will answer them on time. Every once in a while, we'll check the Zoom chat, but I recommend you just to speak out loud. Same holds for you. Okay, and the first part is tree-like graphs and MSO logic. And the second part of the lecture is going to be evaluating first-order logic on sparse graphs. And yeah, this is all very well understood at the time. And if we then have time in the end, we're going to talk about active research area, which is going to be how to translate all these results to the dense setting. So basically the whole lecture is about sparse graphs. Yeah, come in. Hey. So mostly it's about sparse graphs, and the big research question is how to translate it to dense graphs. And hopefully in the end, we're going to tackle a little bit on that as well. And after we're done with the lecture, hopefully you know enough to use these meta-theorems in whatever way you want to use, and perhaps even know enough to participate in active research in the area if you chose to do so in terms of master theses or whatever. And yeah, we're going to also learn some tools to achieve these goals. So we're going to learn some theorems from logic, like Geismann's theorem, Stefan-Wort theorem, or Ehrenfeucht-Rosé and we're going to learn about tree width and how to work with tree width algorithmically. And for the second part, we're going to learn about sparse graphs. It's not so easy to come up with the right definition of what a sparse graph should be, because if you just require that there's few edges, then that's maybe not quite that yet. And yeah, we're going to talk about how to what is the right notion of sparsity, and also while doing so, we're going to dive into some of the core proofs of algorithmic meta theorems. So we're not going to go too deep into the technical details, but I hope to show you, like for the central proofs, some intuition and the train of thought and how to prove these kind of things. And another question is, why should you really care about all this? And the first reason would be that it gives you a very quick and easy classification tool. If you encounter some new problem and you want to know, is it a hard problem, is it an easy problem? The first thing, at least I would do, is try to see in which logic it is expressible. Can I apply some algorithmic meta theorem? And then I maybe see already that it's tractable on a wide range of graph classes, or maybe not. And it can also be quite useful as a subroutine if you're coming up with some algorithms that often there's maybe as a special case, something that you can solve using an algorithmic meta theorem. And why you should not use them is, when you shouldn't use them is when you care about like actually implementing something. So this is a big drawback of these meta theorems, that they have huge hidden constants that make the runtime explode if you actually want to implement them. So think of it more as a theoretical classification tool. And if you actually want to implement them, then you should for sure exploit a little bit more about the structure of your problem and the structure of your instances than just the general purpose meta theorem. So then you probably want to resort to some handcrafted algorithms. And another question is, why do I care about these meta theorems? And I care about them because they're like a big part of some general theory of tractable graph classes. So there's a very active research community trying to figure out what are the most general kinds of graph you can assume, such that a lot of problems that would otherwise be hard are tractable on these graph classes. And in order to measure whether a graph class is tractable or not, a lot of problems should be solvable. And for this, you can classify it using algorithmic meta theorems. Okay, so this is a bit of a teaser. Next, I want to talk about the formalities. So semester hours, there's going to be 2 and 3 credit points. And we want to have weekly lectures on Tuesdays. And yeah, as you see, it's hybrid. Some of you join online, some of you join in person. And the slides will be made available on time. So either beforehand or at latest, they will be made available afterwards with the annotation that may happen during the course. And every 2 weeks, there will be an exercise session. I tried to keep this exercise session very interactive. So the idea is that at the beginning of the session, I'm going to present, let's say, 4 exercises, and then you guys should solve them together interactively, like talk to each other. Somebody comes up with an idea, and the other person iterates on that idea. The third person may find a counterexample where the idea doesn't work, and then hopefully I'm just like orchestrating the ideas, and you guys come to the solution yourself. Which poses a bit of a problem if we're split between online and in-person participation. So I would like this to be everybody together in person here at 11 on Fridays. But maybe if people want to join online, then we do it also online, a separate session, and then you can choose which session to choose from. Maybe it's best if I make an online poll about this. What are the preferences and what are the preferred time slots? Here I wrote that the online session should be afterwards, but maybe it's better to have it before the in-person session. So I will make a poll perhaps about this, and you can tell me about your preferences there. There will be no exercises no mandatory homework exercises, but I may give you some problems to think about at home if you wish to do that. Any questions so far?
When is the first exercise?
The first one will be not this week, not next week, but the week after. I think it was there will be a slide at the end when the first one will be. But I wanted to have like 2 to 3 lectures beforehand, so we have some stuff to cover. How about
Are the exercises mandatory, or is it a problem if we miss one?
Yes, the exercises will be mandatory.
Okay.
So this is what I wanted to talk about next. So the way it works is that you get a passing grade, like a 3 befriedigend, if you actively participate in all the bi-weekly exercise sessions. So I think there will only be 4 exercise sessions, and you should actively participate in those. And this means being present, like in person or online. And it means that you can contribute something to the session, like being familiar with the relevant material is mandatory, and that you should make some meaningful contributions, not just sit in the corner and not say anything. So this is required for participation in this course to get a grade in the end. And if you do that, you already get the befriedigend. And if you have any problem participating, let me know in advance, and then we can hopefully work out some alternatives if you have a good reason that you cannot make it. Yeah. And if you have your passing grade, you may additionally take the oral exam at the end. So this is voluntarily, and you can use it to change your grade. So if you feel like you want to have a better grade, let's have an oral exam, and then you hopefully get a better grade as well. But it's not guaranteed. If you really fail in the online exam, it may also go down. But I hope this will not be the case for anybody. Any questions about this so far? Okay, great. Then let's maybe talk a little bit about each other. So I'm Jan Reyer. I guess we can just go by the first name, so feel free to call me Jan. I did my computer science studies and my PhD at FETH and came here last year. And yeah, I like doing, basically my research is about the stuff that I'm going to teach. So I'm very happy that I can do this lecture. So I like algorithmic meta theorems, parameterized complexity. I like working on structural graph theory and also randomness. And yeah, this is the first time that this lecture is held. So there may be some hiccups every once in a while. And on the other hand, the reason it's the first time it's held, so you can also actively shape how this course works. So if there's anything particular that you're interested in, or something like that, then maybe I can like take it into account as well. So maybe it would be nice if you guys say a little bit about yourself, so I kind of know what is your background and what you're familiar with, or maybe what you're not familiar with, then I can adapt the lecture like that. So maybe the people in the room who want to say something about it, you guys.
Yeah. So my name is Gaspar. I'm here for a semester in Erasmus. I come from a school in France, in Rennes. Yes, so I studied. It's an engineering school, but it works a bit different than bachelor and master. So it's my 5th year of study. And yeah, I studied computer science.
Okay, good. Yeah, nice. How about you?
My name is Loki. I'm just finishing the Bachelor of Software Engineering at TU, and I'm interested in algorithms and logic. That's why I just started the Master Logic and Computation.
Okay, we're gonna have plenty of algorithms and logic here. That's good.
So my name is Franz. I'm a PhD student under the supervision of Fredrik Sirowski, and I'm working on QBF and PQBF.
Yeah, lots of people from the algorithms complexity group here.
Yeah, I'm also a PhD student, same group, but a slightly different topic. So mostly doing graph drawing, which is very removed from this. I've heard about the meta theorem concept numerous times, and it seems like a gigantic hammer that we can whack problems with, and I'm just interested in seeing how this actually works.
Cool.
My name is Renato. I'm also doing in the same group, but I'm mostly working on like the practical or like the implementation side of things, linguistics, technology related to graphs and parameterization complexity. And yeah, I'm also so the one theorem that drew me in was Kusser's theorem. To me, it seems almost magical that it's even possible, and you hear that there's probably more. And that came from his work reading into this course.
Cool.
Yeah, I'm studying logic interpretation, and I'm also still need a few months back because sometimes we use them, and it's like he said, it's just hey, we get it, and now we know that, but we didn't should improve by it's like this works, and that's and it's interesting in this kind of things.
Okay, cool.
I'm working on this one classification. I'm currently writing a field about what this topic of enumeration complexity, but I just like meta because it's like a switch from solving a problem directly to just decoratively explain the problem and then having the solution quite appear.
Yeah, so just to have a quick overview. First of all, thanks of you guys. Yeah, for the online participants, I don't know if I should go through the whole list. If somebody wants to say something, they may say something now. Okay, then maybe a quick poll. Who of you feels like they have a good overview of a logic in general? Like know what first order logic, second order logic kind of is? Okay, that's, I'm not going to assume much about it, but yeah, then we can perhaps cover some parts quicker, and so that's good. So yeah, here's the question you asked, when the dates are. So we're going to have 2 more lectures, and the first exercise is going to start on 29th of October. And I guess now we can get started with a little bit of a crash course. So I want to introduce you a little bit to the philosophy behind meta theorems and structure, and why why it may be helpful to assume some kind of structure in the input. So first of all, this whole lecture is only going to be about graph problems. So this is not really that much of a restriction, because often you can describe all kinds of problems using graphs, and graphs are just very nice. Like you can define and use it to define friendships or conflicts or dependencies or whatever. And on the other hand, it's graphs, you have a lot of room to restrict their structure, using, for example, planarity or by assuming bounded degree. And yeah, if you're into logic, then you can consider the Geifman graph of any structure, and you again get a graph, and you can say also stuff about general structures, not just graphs. And yeah, many problems that would otherwise be hard, they become tractable if you assume a little bit of an extra structure. For example, independent set is hard, but if you assume your input is a tree, then it becomes tractable. Coloring would otherwise be hard, but on interval graphs it becomes tractable. And we're gonna talk a little bit about the independent set problem, and we will observe some behavior that will be very characteristic of the general things that we're going to discover soon. So, refresher, what is the independent set problem? And an independent set in a graph is a set of vertices such that no vertices in the set S are adjacent. And the question is, you have a graph G and some number K, and you should answer whether there is an independent set of size at least K. This problem is, of course, NP complete. Anybody not familiar with P, NP, this whole theory? Okay, that's good. NP complete are the problems which we assume to be hard, and by showing it's NP complete, we cannot really hope for polynomial time algorithm for independent set. But I said we want to exploit some structure, so on certain inputs, independent set becomes indeed tractable. So, and you can solve independent set, for example, in linear time on trees. And the way you do it, maybe some of you know it already, is you root the tree and then you kind of parse the information from the leaves to the root. So at this example tree here, we may have these kinds of tables. In the beginning, we consider just the leaves, and we write down what kind of solutions we can expect. So for this vertex, we see that if we put the vertex itself into the independent set, then we get an independent set of size 1. And if we don't put it into the independent set, then we get an independent set of size 0, if you consider this subgraph that only consists of this single vertex. So it's a very trivial case to start from, and we can do the same thing for all the leaves. And next, we can consider this vertex here, and the subgraph induced by this vertex. And if we put the vertex here, that is now the root, into the independent set, then we get one vertex. But we cannot put any of the children into the independent set because they would be adjacent to it. So we cannot increase the independent set any further. But if we want to be a little bit more precise, we know that this vertex cannot be in there, this vertex cannot be in there, this vertex cannot be in there. And then we look in the table, what happens, what kind of solution can we expect if we don't put the vertex in there, and we see it's all zeros. So we see that we have to add a 0 to the table entry there. On the other hand, we can also decide that we don't put the vertex, this root here, into the independent set. Sorry, I have to wiggle the screen sometimes. So we say this cannot go inside. Then in the subtrees, we have all kinds of freedom that we can choose from. So we may put, we can just take the maximal entry in the tables of the subtrees. So here we see 1 plus 1 plus 1, so we get 3 as the size of an independent set if we exclude this vertex here. And this is how we define this kind of table. If anything is unclear on the way, just feel free to interrupt me. And similarly, we may define a table for this other root vertex. And at last, we combine compute the table for the whole tree by computing the table for the root. And again, we have two cases. If we put this vertex inside the independent set, then we have to exclude these vertices, and we sum up the appropriate tables, and we come up with a value of 4. And if we don't put the vertex inside, we can take the maximum of the two subtables and add them up, and we also come up with a number of 4. And the way we read out the final solution would be by taking the maximum of the table in the root. So this is a very nice concept of doing dynamic programming of the tree to come up with a solution, and something that we're going to ramp up soon by doing this kind of dynamic programming for the whole MSO logic, and this way proving our nice meta theorem for trees, also called Gusselt theorem. But yeah, this is just a first example of how we see problems that are hard in general become tractable if we assume instances to be simple, like trees, for example. But this can in fact be extended to not only trees, but also tree-like graphs. And we're going to define the notion of tree width, and we say that a graph is tree-like if the tree width is very small. So tree width 1 would just capture exactly trees or forests, and higher tree width captures something that looks pretty much like a tree if you close your eyes and squint a little bit. And this leads us to then our first meta theorem. The first half of the course will be about proving Gusselt theorem, which states that every problem definable in monadic second-order logic can be solved in linear time on graphs of bounded tree width. Oh yeah, here's an example of a graph that kind of looks like a tree and has bounded tree width. And yeah, this way you can solve, for example, coloring, independent set, dominating set, feedback vertex set, Hamilton path. They can all be defined in this MSO logic. Here, a quick teaser of what MSO logic can do. You can quantify over vertices and sets of vertices. And then you can have this existential quantifiers and universal quantifiers. And you can have your standard Boolean operators. And you can ask whether two vertices are adjacent or whether one vertex is inside a set. And this is what you can do in MSO. So we're going to have some examples. And the idea is that we say the problem is expressible in a logic if we can write down a sentence in this logic that is true if and only if an instance is a yes instance. So you give an instance, and instead of and you just look at the sentence. If it's true, it's a yes instance. If it's false, it's a no instance. This is our notion of expressing problems in logic. And then if we have such a sentence, we can simply evaluate the sentence, and this then gives us the answer to our problem. So here's an example of the first question there.
Just, I keep forgetting this, but what's the restriction monadic again? Because like this wasn't the full second order logic. It's not
Yes, the question was, what is the difference between second order logic and monadic second order logic? And the restriction is the things you can quantify over. In second order logic, you can quantify over relations, but in monadic second order logic, you can only quantify over sets or edges, instead of quantifying over functions and more complex things. So you can say there exists an edge set or a vertex set, while in the whole MSO, you could say there exists an injective function or stuff like that.
Okay.
And that's too powerful for us. So who can say what this formula here expresses? Yep.
There exists a triangle in the graph,
Yeah, there exists a triangle. So these kind of formulas are read in the way there exists a vertex x1, x and y and z, and then x should be adjacent to y, x should be adjacent to z, y should be adjacent to z. So that's exactly a triangle. Some other example, what did this guy do? People outside on the online world, just feel free to shout out if you want to participate.
That a vertex is connected to other vertices.
There is a vertex that's connected to all the vertices, exactly. So an apex vertex, we also call it. So this so far is second order logic. What does this formula do? Now depends on free variable x. Yep. It expresses that x is an independent set, yes. There should not be two vertices that are both in the set and adjacent to each other. And if you exclude such things, then you get an independent set. Yeah, and with Cosel's theorem, we will show that you can evaluate these kind of formulas. And so that's about the first part so far, about second order logic. A quick crash course. Any questions so far? If not, then let's talk about a little bit different things. So what about planar graphs, for example? We're still going to stick to our independent set example, and we want to solve it. We know on trees it's tractable, and also tree-like graphs, we will also see that it's tractable, but planar graphs are not really tree-like. They can be very spread out, like grids, and thus you cannot really squeeze them into a tree. So what can we say there for the independent set problem? First, we have some bad news. So independent set is NP complete on planar graphs. And now, of course, we could give up and say we can't do anything on planar graphs and go to the next problem, but this is not in the spirit of this lecture. So we're going to make a bit more fine-grained distinction in terms of complexity classes. So some people may argue that just distinguishing between P and NP is a little bit too coarse. So we're going to define fixed parameter tractability. That's, some of you may know it already, others maybe not. And is a tool to have a more fine-grained distinction between tractability problems. To capture the tractability of the problem. And the idea is that even though the problem may be hard in general, we try to identify the instances where it still is tractable. And this is something that we do with a parameter. So every instance will get something that we call a parameter. And the idea is that if the parameter of an instance is small, then we'll still get an efficient algorithm for the problem. And in practice, this can be nice if we observe that many real-world instances actually have a small parameter. That's at least the hope. So let's be a little bit more precise. So the parameterized independent set, in our case, we would parameterize it by the solution size. The solution size was K, So our input would be a graph G and some integer k, and we ask, does G have an independent set of size k? And what we call the parameter will be this number k. What we say now, this is a very central definition that will be important later on, is that we say a problem is fixed parameter tractable, also abbreviated FPT, if instances with parameter k and size n can be solved in some time f of k times n to the constant. So the running time should be the exponent, this constant c, so should be independent of the parameter. So we want to split it up in two parts, and if this function, or if the number k here is small, let's say we're looking for an independent set which is rather small, let's say has size 10, then we're going to hope that this function f of k will also be very small. In particular, it will be some constant. If 10 is a constant, then f of 10 will also be a constant, and we'll end up with a real polynomial time algorithm. So for every fixed k, the running time will be an O of n to the c. So this is a very well-established concept in the field of parameterized complexity. And who of you has heard of this kind of parameterized complexity beforehand? But not everybody, I suppose. So at first glance, this may look a little bit strange, but you could think of it in terms of k is a very small number, and then f of k would also be a very small number, and then you have a polynomial time algorithm. And this is what we call the parameterized independent set problem. We have this additional parameter, and we want to have a running time that is some function of the parameter times some fixed polynomial in the size of the instance. And here again, we have some kind of bad news that independent set is not fixed parameter tractable. And in fact, the best known algorithm for independent set has running time n to the k roughly. And this is not something we want to do. We want the k to be in the function before the polynomial, but the degree of the polynomial should be independent of k. And this kind of algorithm is the trivial algorithm that you would expect. You just iterate over all sets of size k. So you have for all v1 in v, for all v2 in v, for all vk in v. So you have iterate over all sets of size k, and then you check whether these k sets induce an independent set. And this way you can check whether the graph has an independent set of size k, and running time n to the k, but it's not an FPT algorithm. So now we have two things. We have parameterized complexity, and we know that we cannot express it in FPT time. So this is under the assumption that FPT is not equal to W1, which is like an assumption similar to P is not equal to NP. So it's some complexity hypothesis, and we assume it. It's very reasonable to assume it. Everybody assumes it. And so we cannot solve it in FPT time, and we also cannot solve it on planar graphs in general. And now the thing that is common to do is we combine the two approaches. So we want to solve parameterized independent set on planar graphs. And here we're going to have some success. So we can show that parameterized independent set is fixed parameter tractable on planar graphs. And let me give you a quick sketch on how such a proof may proceed. So we want to find an independent set of size k, and k is rather small. And there's a nice theorem that on planar graphs, you can always find the vertex with degree at most 5. So in this example, we have the vertex v here, and it is in the graph, it has degree 4. And we can do the following. We're going to consider not an independent set, but a maximal size independent set. So an independent set where no vertex can be added such that it's still an independent set. And we notice that at least one vertex from this neighborhood has to be included in this independent set. because if this vertex is not included, if this vertex is not included, and that vertex is not included, and that neither, then we could make the independent set a little bit larger by including V in it. So a maximal independent set has to include one of those vertices. And we're going to make a guess. We're going to make some kind of branching algorithm, and we guess the vertex that will be inside the independent set. So we have to try out 5 or 6 different options, because we know that this vertex V has only 5 neighbors and the vertex itself. So we're going to try out all 6 options, and we're going to just guess, okay, this vertex, let's say W, will be in the independent set. And then we only have to find k minus 1 vertices. And we're going to just recurse and continue this approach. And if you can draw it as some kind of tree, as some kind of computational tree, start at the root, and then you branch into at most 6 options. And while branching, you fix one vertex of the solution. And you again going to branch into at most 6 options. And in the end, after k steps, you have picked all your k vertices of the independent set. And you're going to check, is it a solution or not? And if it is a solution for one of these computational branches, you have found something. And if none of those computational branches lead to a solution, then you know for sure that there is no such thing. Is this clear so far? If you're not familiar with parameterized complexity, this may be a bit too much to take in. What do you guys think so far? Okay, good so far. If anything is unclear at some point, feel free to just jump in. So if you want to formalize this as an algorithm, it will proceed as follows. Independent set for a graph G, it's a parameter k. First, we check if the graph is empty and k is 0, that's our base case. Then we can return, and otherwise we find this vertex with low degree, and we try out all vertices in the closed neighborhood, and this gives us 5 computational branches. We recurse there, and if any of those branches where we decrease the parameter by k give us a correct answer, then we know there is a yes, it is a yes instance, and otherwise we return false. And this algorithm solves the problem in 6 to the k time, and 6 to the k comes from the fact that for each recursion we branch 6 times, and the depth of the recursion is at most k. So we get a branching tree of size 6 to the k. And this is an FPT function. And now we can summarize a little bit on where we stand so far. We notice, I want to talk about sparse graphs. So we notice that trees have a small number of edges. So a tree on n vertices has at most n minus 1 edges. So it doesn't have a quadratic number of edges, but a linear number of edges. And similarly, planar graphs, you can also show that they only have, I think, 3n many edges. So they could also be considered sparse. And we just noticed that parameterized complexity of independent set is tractable on planar graphs. And you may wonder whether you can push this up further. If you could say something like, the problem is fixed parameter tractable in general on some kind of sparse graphs. And so for this, we can also ask ourselves, do problems in general become simpler if the graph is sparse? And the question is kind of yes and no. You have to think about what is the right notion of sparsity. So planar graphs are sparse, but you can't just require that the graph has few edges. You can do some tricks there, and problems are hard on these kind of graphs. And we will discover the notion of sparsity theory, which will give a more detailed answer to this kind of question, like what are sparse graphs and what kind of problems can you solve there. What we will tease us so far is that nowhere dense graph classes are at the top of the sparsity hierarchy. So if we have planar graphs here, then nowhere dense graph classes are more general than planar graphs. And the kind of argument that I showed you before, how to solve independent set on planar graphs, you can push it all the way up to nowhere dense graph classes. So if we want to quickly sketch what the second result of this lecture is going to look like, it's going to be as follows. We show that every problem definable in first order logic can be solved in FPT time on nowhere dense graph classes. And this basically is a parameterized version of the result that we discovered already for tree-like graphs. So on tree-like graphs, you can solve independent set efficiently. And now we're going to show that you can solve parameterized independent set, for example, efficiently, or parameterized clique problem, or parameterized dominating set. And here the parameter is always going to be the solution size. So if you're interested in finding an independent set, clique, dominating set of small size, then you get an FPT efficient algorithm on nowhere dense graph classes. And the picture that we painted so far for independent set looks like this. We know that it's hard in general, but on trees, we can solve it in linear time. And so here, this is the first circle trees. On the other hand, on planar graphs, we cannot solve it efficiently. That's where we go back to parameterized complexity. And we see that on planar graphs, we get a fixed parameter tractable algorithm. And then for the general case, we can't say much. It is even hard in parameterized complexity in the general case. And this kind of behavior, we're going to observe it generally for many other problems. And for this, oh, sorry, was the screen off for some time? I'm sorry. Yeah, so we gotta define the notion of bounded tree width and nowhere dense. And if you don't know what this is so far, then you can think of bounded tree width generalizes trees, and nowhere dense generalizes planar graphs. And then you get a similar picture for our independent set problem. On bounded tree width, you can solve it in linear time on nowhere dense class.
We don't see the screen.
Oh, sorry. Seems like the screen went off and damn it. Trying to turn on the projector again. Okay, now it looks good again. Okay, so okay, what was I saying? Okay, on bounded tree width, you can solve the problem independent set in linear time. Then on nowhere dense graph classes, you can still solve it efficiently with respect to parameterized complexity. And on the general graphs, you can't say that much. And I think we already reached the end of this first lecture. So, so this is this kind of complexity behavior for independent set. We're gonna generally observe it for many other problems, and we're gonna find out that here on bounded tree width, you can efficiently evaluate MSO logic, and on these sparse graph classes, you can efficiently evaluate FO logic, and these are gonna be the main results of this lecture. And then later on, if we have time, we're gonna translate it to dense graph classes as well. Like the dense analog of bounded tree width would be bounded clique width, and yeah, hopefully I can talk to you about these kind of results as well. So this time we finished a little bit earlier than the 1.5 hours that have been allocated to it. Are there any questions so far? Yep.
Main one. So this is like problems are solvable if they're expressible in a certain logic on graph classes with a certain property. What if you're like, are there similar results for problems where the input is not a graph, but you can still structure it and give it some properties?
The question is, what if the input is not a graph, but you just want to still assume some kind of structure on the input? So one way to go would be to assume that the input is not a graph, but any logical structure that you may assume. So you have some elements and some relation between these elements. Like a SAT instance, for example, can be written as a relational formula. And then you consider, or you may consider the Geithman graph of this structure.
Basically, turn it into a graph.
You can turn it into a graph and then have these same statements again.
Okay.
But I'm not that familiar with meter theorems that avoid talking about graphs in general. Usually you talk about them first.
Okay.
Another question there?
Yeah, you can pass on the frequency there until one, where there's a theorem. For twin width, you know, is it the same or the width graph or?
Oh, he's talking about twin width, a recent development, and twin width is kind of very different compared to the notion that we have so far. It kind of goes orthogonal, like this. It is incomparable to bounded tree width and lower dense graph classes. So twin width contains some very general expander graphs that are not covered by the notion of lower denseness. On the other hand, twin width does not contain even all graphs of degree at most 3. So it's a little bit strange. But yeah, it's very interesting. And this is a big open question so far, how to incorporate. It does contain bounded tree width, exactly.
Okay. But you know, formulation the same with the lower dense graph, so it's the same problems divided meter, which then
yes, on bounded twin width, you can evaluate first order formulas. Yes. Mm-hmm. You can even evaluate ordered first order formulas if you assume some additional order on the input, but that's a different question. Any other questions so far?
But click width is not nowhere dense.
Click width is not nowhere dense, exactly.
So also like a form to the hierarchy
so click width corresponds to MSO transduction of tree width. So there's some kind of link between tree width and click width, but these MSO transductions blow it up further, and it's not nowhere dense. It can contain very large cliques, as the name suggests, but it is still contained in twin width.
Yeah.
Any other questions so far?
Could you explain the difference between monadic second order logic and second order logic?
Okay. If not, then thanks guys for coming. Oh, there's a question, somebody raising a hand.
Hello, can you hear me?
Just speak out. Okay, maybe it was just a clapping emoji and I didn't see it correctly. Okay, then thank you very much and see you next week.